Um, I wanted to just finish the morning talk since we had many questions during the talk. I didn't want to rush in, but I also feel that we've covered so much about Majorana fermions without basically reaching the punchline. And I asked the organizers to give me maybe 15 minutes of time to explain why is Majorana zero modes are so important and why they are so useful for quantum computation. So before I go in, I'll just remind you that, well, they're characterized by this degeneracy. So there is ground state degeneracy. There are these zero modes at the opposite ends of the wires. Another interesting effect is associated with the Josephson effect. And because we have this ground state degeneracy, there's a new possibility now that the charge transferred between two superconductors in units of E instead of units of 2E. So conventional Josephson effect, right, will have 2 pi periodicity. And what does this mean, 2 pi periodicity? It means that in some units, the charge tunnels coherently from one superconductor to another superconductor in pairs, so 2E charge tunnels. So you can imagine that there is a virtual process when the electron tunnels first and then the second electron tunnels first, and that completes the cycle. But in these topological superconductors, there is now a new possibility where you have these zero energy states. So even a single charge, when it tunnels, it's actually a real process rather than a virtual process. And it turns out that it's a coherent process. And it's very remarkable because now we have a new periodicity. New fundamental periodicity, which is 4 pi instead of 2 pi. And there is very simple exercise one can do, which I outlined here. You just take 2 Kitaev Majorana chains, assume that there is some phase difference between these chains, and assume that there is some normal wire, uncovered semiconductor wire in the middle, and just compute the spectrum of these Andreev bound states in this region. So in the topological phase, you see, indeed, this is what one finds, that the spectrum sort of goes here, and then at this point, it turns out that there is a true level crossing. So this true level crossing is protected by the symmetry, and so one cannot open a gap in the spectrum here. And therefore, one should think that this level basically extends from 0 to 2 pi, and then we need to go another 2 pi to go down and return to the same position. So that's basically 4 pi periodic Josephson effect. Now, to contrast with the conventional spectrum, we just simulate this phase transition, and so we we compute the spectrum before we reach this topological phase, and it turns out that the spectrum is 2 pi periodic, so you just follow this line. So basically one can distinguish by just going across the transition, distinguish two phases by measuring the Josephson effect. And that's additional to Majorana zero energy, to the zero bias anomaly I discussed before. So this is very important for quantum computation, and here I just wanted to show that, well, the way to measure it is to measure Josephson current, which is a derivative of the states, and obviously some states will have some slope here and some states will have extremas, so the current will either vanish or be at maximum at these points, and so exactly at those points one should be very sensitive to these features.
The ground state parity changes?
Yes.
So at phi equals pi, can I sort of interpret it as an open chain line in some sense?
Well, this is open chain. So actually, there are 4 Majoranas, but 2 of them don't play any role in some sense. So you have one wire, and you have another wire. Okay. So there is gamma 1, gamma 2, gamma 3, and gamma 4. So I can encode the logical qubit in terms of parities, fermionic parities, right? And then it will turn out that, well, these parities, of course, they will involve the other states because I need to have, I need to be able to exchange fermion numbers. So the two states at the crossings, they will correspond to different fermion parity. But of course, we have to preserve overall fermion parity, right? So these states at the ends will provide you this degree of freedom so that one basically cycles between states 0, say 0, whereas this state 0 encodes, the pair here, fermion parity here, and this, the second one encodes, so this is, say, 2, 3, and 1, 4, and then you go between states 1, 4. So if both of these states have the same even parity, but of course locally, what changes in the spectrum is that you go from a state with 0 parity to a state with 1 parity. And provided this distance is large enough, these other end states, they don't matter. But basically, that's the reason there is this protected level crossing, because as long as you don't change fermion parity, we cannot mix these states. Okay, so but if you do have some processes for some reason that mix fermion parity, then rather than going up like I was showing at some time scale tau r, which is relaxation, what will happen is that there is some process which will relax down to the ground state. So in that case, that tells you that thermodynamically averaged supercurrent will be 2 pi periodic. So there is no there are no signature in terms of the thermodynamic current, but there are signatures when one measures AC current. Okay, and well, here's a simple way of measuring. It's just some schematic, and anyway, I can skip this. Another important ingredient is interferometry. So topological states, I was arguing and proving using this Kitaev model that local terms in the Hamiltonian that one can add, they don't see different fermion parity states, so they cannot distinguish between them. But one can read out the fermion parity by doing some non-local measurements, and such a measurement is interferometry. So if in fractional quantum Hall states, interferometry is used to measure topological charge in the middle. So one may ask if there is an equivalent in superconducting systems. And it turns out that there is an equivalent, and this interferometry involves the Aronow-Kasher effect. Okay? So Aronow-Kasher effect is a dual to Aronow-Bohm effect. So in Aronow-Bohm effect, you are measuring charge around some flux, right? And there is a Aronow-Bohm phase picked up by the particles. Where in this case, we will be doing the dual thing. We will be moving fluxes around the charge. And again, there will be some phase in analogy with Aronow-Bohm effect, right? So this can be done in a flux qubit in the following scenario. So you have 3 Josephson junctions, and there is some flux, and flux is tuned to some value where there is degeneracy between counterclockwise and clockwise currents flowing in the flux qubit. And then, if this junction is very strong and the weak links are here, these two clockwise and counterclockwise currents will be mixed by some quantum fluctuations effects, which are essentially induced by the charging energy of the island. And so that means that these fluxons will be coherently tunneling back and forth through these weak links. And so if we place some charge somewhere in the middle, then these fluxons, which are tunneling through these junctions, essentially will represent some kind of a loop, and they will pick up the phase, the Aronow-Kasher phase, going through this loop. And this phase will be proportional to some offset charge, but also to the topological charge carried by this Majorana mode. So it will measure fermion parity. And what is important for quantum computation is to have a possibility when we have a qubit here. So we will add 2 more Majoranas, and we will measure overall fermion parity of the system.
Have these experiments been performed?
With the wires, they haven't been performed, but in flux qubit communities, they performed routinely. And people have measured this and studied this.
Are they more conclusive than the fractional quantum Hall interferometry? Is this sort of
Fluxons? Yeah. This
Yeah.
is just, I think by now it's very standard.
okay.
So the tunneling of fluxons has been characterized very well in these devices. Okay, so now we basically have all ingredients to do quantum computation. And I wanted to show you why topological quantum computation is different from conventional quantum computation. So first of all, we will just make these wires. There are gates beneath these wires, and ideally one can just change the position of the gates, which means we are changing the topological region versus into non-topological region, which means we are moving domain wall. So just by changing the gate beneath the wire, we will be moving the position of these Majoranas. The second, of course, we need to create some kind of network. And if we create the network of the wires, then we can braid these quasi-particles. And since I mentioned they have non-abelian statistics, there are some exact gates that one will have. And another important ingredient, which I'll explain explain in a second, is the ability to couple these wires to some conventional qubits, and in this case I will discuss semiconductor double dot qubit. And so what's great about these Ising anyons is that they're very robust and one can use them as a memory. And so if we have some good scheme to do quantum computation, then we can shuttle this information to topological degrees of freedom, and we can use them as quantum memory. Okay, so you probably heard this from Professor Bonstill's talk that Ising anyons, they have non-abelian statistics. And one way of understanding non-abelian statistics in Ising anyons is the following. So, as you know, the superconducting order parameter has to be single-valued, right? That's the condition that we impose when we quantize the flux in a vortex. But the Bogoliubov quasi-particles, these U and V's amplitudes, right? They are sort of a square root of the order parameter. And therefore, there is certain ambiguity in their definition. So you can imagine that U goes as e to the minus phi over 2, V goes to as e to the plus phi over 2. And so when we go around and change the phase by 2 pi, there's ambiguity between 2 pi and minus 2 pi. And so in order to define them, we have to put a branch cut somewhere. And so these are my branch cuts, okay, for these 4 Majoranas. And the rule of thumb is that whenever one quasi-particle crosses the branch cut, it picks up the minus sign, okay? And that's basically what will happen here. You see that only one of them will cross the branch cut, and therefore only one of them will change the sign under exchange. So this braiding, non-abelian braiding statistics actually amounts to the simple rule, just the change of operators into gamma 1 going to minus gamma 2, and gamma 2 goes to plus gamma 1. So I have to say that this is just contribution from monodromy, so basically from the defining single-valuedness. There might be also Bayer phase contribution, since these states evolved along the past, but it turns out for these systems, more precise calculations show that the Bayer phase basically vanishes, and you're just left with monodromy contribution. So now the operator that implements this evolution is this operator, and one can see that we can do the following operations. So if you start with the state n1 and 2, where n1 is a fermionic mode here, and 2 is a fermionic mode here, then we can have pi over 2 rotations. We can have some non-trivial operation that actually leads to a different state, and then another pi over 2 rotation. So let me recapitulate. If we encode our qubit in 4 Majoranas, we can do the following operations. We can exchange these two. Again, this is just a pi over 2 rotation. And we can exchange the Majoranas that belong to different pair. And that's equivalent to having a Hadamard gate. And these operations, they are just determined by the quantum statistics of the system. Therefore, they are very precise. There cannot be any errors in this manipulation. And so that's the real advantage. Yes.
What do you mean by exchanging them? They are localized modes at the end.
So if you, I showed you the wires, the slide in the wires, and you see in this sketch you can move them around. So imagine I move this guy here, then move this guy here, and then move them back. So I've exchanged them in the network. That's what I mean by.
So you always need a vertical line to.
Yeah, I need to have at least T junction, 4 junction or T junction in order to avoid so that they don't collide directly, right? In 1D there is no well-defined statistics but in quasi 1D, which is this network, or that's well-defined. It's almost like a 2D system, except we can go along certain paths.
Is there any proof that this is universal? Like if you, this is equivalent to just exchanging them.
Yes. So these guys worked out the details, and so you can take a look. You do a great job. One advantage of this system is that the wave function is very simple, so you can actually work out the details and show that it's cool. Exchanging works.
Why can't you move them through each other?
Well, there's ambiguity, right? So we can think about it as a particle as some kind of singularity. So when two singularities collide, then there is ambiguity.
But but on a real nanowire, like it always has some thickness, so like maybe they can just move around.
Well, I think there is. Well, okay. First of all, when you bring them close together, they will get split.
Okay.
So they form some state. So you better keep them far away and move them adiabatically so that there are no other phases, no other effects. So anyway, so these are the two operations that are protected. Unfortunately, that's not enough because it just generates Clifford gate set. And so what we need to do, and this is not a computationally universal gate set, what we need to do, we need to supplement them by some other non-universal gates. And one of those gates is the so-called T gate, which is pi over 8 rotation. But it turns out that we just need a single non-perfect gate to turn the set into universal quantum computing. And from the point of view of error correction, we just need to error correct one gate out of all the other gates. And it turns out that there is a very high threshold. So the error threshold is 14% for this one gate. One can use some error correction methods to purify the state and reduce the error. So that's a big advantage over conventional quantum computing schemes where you have to have errors down to 10 to the minus 3 level.
How is the error threshold defined?
Well,
is 1%?
So you have some target goal, you have some target goal, and you are asking, what's the error rate that I can tolerate in this single qubit gate?
Is it better to have this number larger or smaller?
Oh, ideally you want to have this number as small as possible. So what I'm saying, for conventional qubits, this number is 10 to the minus 3. So the ratio of the decay rate over clock frequency should be 10 to the minus 3, okay, which is much less than 1%. But here you can tolerate as much as 15%. So that's much easier to satisfy than the requirements for coherence in conventional qubits. So how can we generate these unprotected gates? There are different methods, but I want to focus on this one because I think it's actually quite nice. And that's the idea of this topological quantum bus. So interferometry measurements, they allow one to, this fluxon tunneling between these two junctions, as I said, it couples to the charge in the middle. So we can imagine that there is this Majorana wire network, and there is a fermionic mode shared here, but also we have some charge qubit where charge sort of tunnels coherently back and forth, and that's your two-level system. Okay? So then when we measure the state, the combined state of the system, we will collapse the state to some combined overall fermionic parity state, and that serves as entanglement measurement between two subsystems, between topological and non-topological. So in particular, one can design this protocol where we first shuttle information here, start with some state in this flux qubit, then do a projective measurement, then shuttle information here, then couple the topological and non-topological qubit, and then again do another projective measurement and teleport information basically from this end to the other end. And I think this is one way of making the quantum computing with these Ising-Anion Majorana quasi-particles universal. And I will conclude with just showing this picture. That's maybe the picture. There is some cryostat. Of course, this happens at very low temperatures. But if it happens when we can address very important goals, who knows? So I will stop here.
How important, like in practice, how important is it to have a universal set of gates or whatever it is? Like in practice, maybe there's some useful computations you can carry out just with the operations allowed by exchanging Majorana fermions.
Yeah. So the Clifford gate set can be efficiently simulated on classical computers. So we don't gain much from that. But of course, you're right. There are some applications that are already available. For example, D-Wave machine that I mentioned in the first lecture. It's a machine that's doing quantum annealing. So it's not universal quantum computer. It's a machine that's supposed to solve a specific task. But the task that is very important, it's a task where we start with some number of parameters, and we want to minimize some cost function, and we want to find the optimal solution to some optimization problem. And that is, of course, some application, but it requires less precision, less resources than the fully fledged universal quantum computer.
What's the estimated resource needed to build like a C0 gate with Majorana fermion and this quantum bus gate?
Sorry, once again.
Okay, so how many Majorana fermions do you need plus this phase gate to build something like a C0?
Very few. I mean, few gates, so it's not.
It's not very large.
It's not very large. Actually, there has been a lot of progress recently in trying to understand how to optimize different codes, and people are in fact, developed the whole software schemes. It's a software package called Liquid, where you just put in the algorithm that you want to do, and this package sort of optimizes the number of gates. And they have clever tricks how to minimize, and so they are, these gates are not, the number of operation is not very large. As a matter of fact, I can give you this, that the state of the art for doing quantum chemistry on a system which has maybe 100 to 1,000 logical qubits has been recently improved by 10 orders of magnitude. So from something that was very impractical, using some clever tricks, we optimized these operations, and now it looks very, very practical and very, very promising, because it seems like the number of operations does not scale in a very crazy way with the system size.
So my question is related to something very fundamental in condensed matter experiments. So these are emergent excitation, and generally braiding each other around each other is a very important component of it. So throughout the history of condensed matter experiments, has there been any example of observation of any statistics of these emergent excitations?
Well, they had, okay, good question. So certainly non-abelian statistics was not observed.
No, even abelian is not.
But I think even abelian is not observed. And even right now, people are going back and trying to refine the experiments on fractional charge. So
But fractional charge is reasonably well established in a sense that the short noise signatures in fractional quantum.
no, but recent experiments actually show that, you have more, the charge basically that you get at the edge is random in a sense. So there is controversy in the fractional charge even measurement.
So my question, if I be more specific, so my question is this, that if you want to braid an emergent, let's say, fractional excitation around another excitation, so is it possible that the flux probe will always measure the electron charge, no matter how,
Well, I mean, if you are asking whether it's possible in principle to measure non-abelian statistics, I think it is possible.
means abelian, let's say if you have a 1/3 fractional charge.
Well, you see, the problem is that quantum Hall states, we're going a little bit away from Majoranas, are very complicated states. These are fundamentally interacting states. We don't understand what happens at the edge. There are models, but there might be some modes which are counter-propagating modes, right? So there is edge reconstruction. So in many cases, we actually don't know what happens in the experiments. And that's the main difficulty, that we think we know the theory, we're trying to fit the experiment to the theory, but we actually don't know what happens at the edge. The recent experiments, as I said, there is a new set of experiments from Weizmann group, Heiblum. I mean, they showed that basically the measurements of fractional charge are very tricky, and they can get anything from E02 to E04. So
in a more general sense, is it possible that braiding measurement will always probe the underlying system from which the excitations are emergent from, not the emergent excitation themselves?
I would hope that not, but I would hope that one day we would measure non-abelian statistics and measure fractional charges. And I think the key is to have a very simple system for which you can do very precise computational or analytical modeling. And you want to ensure that whatever is in the experimental lab is in one-to-one correspondence with the theory that describes it. And then we can make very good comparisons. So I certainly hope that this change of minus sign is a real effect, and then there are very specific schemes, very simple schemes, which involve a dozen of these Majoranas to measure non-abelian statistics. And I think that's going to be probably next 5 years, I would say. Because to measure non-abelian statistics, it's much easier than to do quantum computation in some sense, at least in these systems, because we can do statistical analysis. We can collect a lot of statistics, right? Whereas here in quantum computing, you want to have precise gates and things like that. So even if there is something not very perfect, even there is a soft gap and there are some problems, I think statistical measurements will allow one to measure things with certain confidence interval. Okay, guys. Well, thanks for letting me finish what I started in the morning.